I am Anil Kumar. Welcome to my series on trigonometric identities. We'll start from the very basics, and that will form the foundation for you. In case you want to learn from me, you can always send an email on the address given. Also, check our website for the latest videos. What you see here is a list of formulae which are very important to prove trigonometric identities. I'd like you to pause the video at this stage, take a picture of this page, or you may take a note of these formulae. We are going to prove them also in this particular video and then take up questions which will use these identities to solve those questions, right? So we'll begin with the very basic identity, which is called the quotient identity. Tan theta is the ratio of sine and cosine. Cotangent is the reciprocal of tan, which is the ratio of cos and sine. Now, the reciprocal identities are the secondary ratios. Cosecant theta is 1 over sine theta, secant theta is 1 over cos theta, cotangent is 1 over tan theta, right? Then we have the Pythagorean identities, which are sine square theta plus cos square theta equals to 1 plus tan square theta equals to secant square theta, and 1 plus cotangent square theta is cosecant square theta. We'll prove these identities using a very simple method. Now, these identities can be rearranged. Many times, to prove identity, we should be writing most of the trigonometric ratios in terms of sine and cosine. In that case, sine square theta plus cos square theta equals to 1 becomes your primary Pythagorean identity. Now, this can be rearranged. You could write sine square theta as 1 minus cos square theta. Now, using difference of squares, we could always write this as 1 plus cos theta times 1 minus cos theta. Do you see that? So we converted sine square theta into a factored form. This factored form helps to simplify. We could do the same with cos square theta, writing it as 1 plus sine theta times 1 minus sine theta. Well, this kind of operation could be done by secant and the cosecant identities also, as shown here. Now, another important thing about secant square theta minus cotangent square theta plus 1 is, which we are talking about the second identity, if I take tan to the right hand side, then we get secant square theta minus tan square theta equals to 1. Now, this is the difference of square, which can be written as secant theta plus tan theta into secant theta minus tan theta equals to 1. That means I could write secant theta plus tan theta as 1 over secant theta minus tan theta. This is extremely important. Similarly, I could write cosecant theta plus cotangent theta as 1 over cosecant theta minus cotangent theta. Now, these are very important results which we are trying to understand right in the very beginning. Now, these really help to solve or to prove trigonometric identity. Then even an odd function, sine, is an odd function. That means sine of minus theta is minus sine theta, and cosine is an even function. That means cos of minus theta is plus cos theta, right? So this is very clear from the cast rule. In the cast rule, you know that cosine is positive in quadrant 4, where theta is negative. So the value is positive, correct? As it is in quadrant 1, right? So that is a rule which you have to remember, and that helps you to prove these identities also. And then we have the cofunction identity, which is when you're looking at a right triangle. Let me just make one to make you understand. So if we have this right triangle, in this we have a 90 degrees angle. If one of the angles is, let us say, theta, the other angle will be what? Well, this angle will be 90 minus theta, correct? So this angle is 90 minus theta. So from here you can see that sine of 90 minus theta will basically will be the ratio of these two sides. Now these two sides ratio is cos of theta, correct? So very simple to visualize the cofunction identity. Similarly, the related acute angle identities can be looked into. So I hope you got a good foundation, and now let us see what type of questions we are going to solve to begin with. Now these are relatively simple questions. So we have these 6 questions. The idea here is to understand 6 different strategies which should be applied to solve trigonometric identities, rather, prove the trigonometric identities. So the question will be prove trigonometric identities. The very first one here is sine square x cos square y minus sine square y cos square x equals to sine square x minus sine square y. The second is sine to the power of 6x plus cos 6x is equals to 1 minus 3 cos square x sine square x. Question number 3 is sine square theta plus 2 cos theta minus 1 is divided by sine square theta plus 3 cos theta minus 1 equals to cos theta over cos theta minus 1. 4. 1 plus cos theta over sine theta plus sine theta over 1 plus cos theta equals to 2 over sine theta. Then we have tan theta minus cotangent theta divided by cos and cotangent is equals to tan square theta minus cot square theta. And then we have something to do with radicals. Now, let's try to understand the strategies which we could use to solve such questions, correct? So the strategies could be that in this particular case, we could use the Pythagorean identity, correct? So, since we know that the right hand side is only sine terms, so the cos terms could be written as sine terms, right? You get the idea. So basically, you could say, well, cos square theta is equals to 1 minus sine square theta. So if you do this identity, then you're able to solve the question very easily. The second one here may require a strategy of cubes, right? Do you know what is a cube plus b cube as? Well, you could factor this as a plus b times a square minus ab plus b square. Once you factor like this, you will get your result. The second one here, third one here is sine square theta plus 2 cos theta minus 1. We want the results in terms of cosine. So it's a good strategy to write sine square theta this time in terms of cosine, right? So we could write this as 1 minus cos square theta. Perfect. That should help you to solve this one. Here we could take a common denominator, cross multiply, and then simplify. So common denominator is a good strategy. Perfect. Now in this particular case, you could rationalize. Here also, whenever you see square root is a good strategy to rationalize. When we say rationalize, it means what? It really means to multiply and divide by the conjugate. Well, in case you have tan and cotangent, you could also do is convert to sine and cosine, right? So that is another very good strategy. Convert to sine and cosine, correct? Perfect. So applying these strategies, you should be in a position to solve these questions. Now, let's begin our lesson. We'll now understand what the trigonometric identities are. Well, here is extended questions. Many times while proving trigonometric identities, you're also involving equations. So here what we see is the combination of identities and equations. After learning all the concepts, we'll actually take up these questions. Perfect. You can at present pause the video, take a note of these questions. Perfect. Now, let's begin with the basics, and that is, after all, what are identities and what are equations, and how are they different? Well, an equation is a mathematical representation of a statement where two expressions are equal. For example, f of x is equal to g of x. This is an equation. Now, this equation could be true for some values or could be true for all values, or this equation could be always true. Correct? So, this is an equation where f of x and g of x are expressions with independent variable x. So, when we say f of x, x is the independent variable. So, both are dependent on x, and this means we need to find those values of x for which the two expressions, one on the left side, the other one on the right side, are equal. Correct? If the equation is true for every value of the variable x for which both expressions are defined, then it is an identity, right? You see the difference between the two. So, identity is an equation, but identities are true for all the values in the domain of the function, correct? You get the idea. Hmm. Otherwise, we'll treat this as a conditional equation. Well, conditional equation in general is an equation, right? Just to differentiate, we'll call identities which are true for each and every value of x, the independent variable. Now, here is an example. Example here is you need to identify the identities from the given equations, correct? So the question here is explain why set A of equations are conditional equations and the equations of set B are identities. We are saying that set A are conditional equations, correct? And set B are identities. You need to explain why, correct? So take a note. 2x minus 1 equals to 5, x square minus 8x plus 7 equals to 0, x plus y equals to 0, x square equals to minus 1. So these are the four equations. You will note that this equation here, 2x minus 1 equals to 5, has a solution, which is x is equal to what? You can take 1 to the other side and divide by 2. It is only true for x equals to 3. So this is an equation which is true for one value. This is a quadratic equation, x squared minus 8x plus 7 equals to 0. Now, 7 times 1, correct? So you could factor this as x minus 7 times x minus 1 equals to 0. So it has two solutions. One of the solution is 7, the other one is 1. X plus y equals to 0 could be written as y equals to minus x. See, this particular equation is true for infinite values, right? Infinite values. It is a straight line. Let me just draw it here. Very interesting. We have y equals to minus x, which is a straight line. Now, this particular equation, it is not an identity, correct? You need to justify why. Y equals to minus x, right? You need to justify why it is not an identity, but it is an equation. It has infinite solutions, right? You get the idea. Well, for an identity, any value of x which I put should work. But here we have only coordinate points, right? We have coordinates as solution, right? Do you understand? Not each and every value of x independently. Do you understand? We'll elaborate on this also. For example, when we talk about these identities, I'll tell you how they are different, right? Now, the next one here is x squared equals to minus 1. This one has no solution, right? This has no solution. But still it's an equation. Equation may have a solution, may not have a solution. It may have one solution or many solutions, correct? That is what we have learned in this particular part of the video. Now, as far as the identities are concerned, you can see from here 3p plus 5p is always 8p. P could be any value. You can write p as 0, 1, minus 5, whatever you want. X square minus y square equals to x plus y times x minus y. For any value of x and y, this is true. You understand? If I put x equals to 5, for example, and let's say y equals to 1, even then this is true. You get the idea. But if I select a value like this, x equals to 5 and y equals to 1, this is not true. This is not true. You get the idea? This is only true if I put x equals to 5, then y is equals to only minus 5. Y cannot be equal to 1, right? You cannot work the other way. You cannot put y equals to 1 and x equals to 5 and show that both the sides are equal. No, they are not. So therefore, this is an equation, whereas here we have an identity. You get the idea? You can put x equals to 5, y equals to 1 in this, and you'll find that left side is equals to right hand side. So that's an identity. Perfect. Now the next one here is important. X square minus 1 over x plus 1 is equals to x minus 1, provided x is not equal to minus 1. There could be a restriction in the identity, right? So note, identities can have restrictions. Clear? So, it is only that the identities are true in their domain. Perfect. Now, here is another very important question for you, which is square root of x square equals to x an identity? Hmm? Justify your answer or provide a counter example. Now, providing a counter example is one of the most efficient ways of proving or disproving something, correct? Right. It is mostly used to disprove. Now, we can provide a counter example. In this case, if I put x equals to, let us say, minus 1, then we know minus 1 square root is equals to 1. It is not equal to minus 1, correct? So, it is not an identity. You get the idea. Identity actually is that square root of x square is equal to absolute value of x. Now that becomes an identity. So this is an identity. You get the point, right? So that is how we could actually differentiate between the two concepts of equations and identities. Perfect. Now this is an equation which is only true for x greater than or equal to 0, not for all values of x. So I hope with this you got a clear idea of what is an equation and what type of equations could be identities. Now let's get back to trigonometry. Trigonometric equations will definitely involve trigonometric expressions. So let's look into that part. So we'll now see how do we prove trigonometric identities. Well, we began with a very simple thing, which is what are primary trigonometric ratios. Sine theta is b over r. If we consider a right triangle, correct? So here we have a point P in a coordinate plane. So in a coordinate plane, we have a point P which is AB. Let me just make a bigger diagram here. So this is how I'm going to represent this. So on this coordinate plane, we have a point P which is being written as A and B. Well, that is the point origin, right? Okay, so let us say that this Q is the projection of P on the x-axis, right? So let us say that this is the projection on the x-axis, and that's the y-axis. Okay. Now, when I say that this is the point P with A and B, that really means that this part is A and the vertical distance is B. And let us say this angle is theta. Now, in that case, we can define our trigonometric ratios as B over hypotenuse. This value R, the hypotenuse, will be using Pythagorean theorem, a square plus b square square root, as written here, right? So for any point P, A, B, we would have a hypotenuse whose length will be a square plus b square square root. It is always positive, correct? Now, the ratios we could always write as SOHCAHTOA, right? Sine is the ratio opposite to hypotenuse, cosine is adjacent to hypotenuse, and tan is opposite to adjacent. So you can remember as SOHCAHTOA, right? Trigonometric ratios which when flipped give rise to secondary trigonometric ratios as shown here. Cosecant theta is reciprocal of sine theta. Just flip r and b, right? You get your ratio. So accordingly, you get all the six trigonometric ratios. Now, to prove them that they are true is very easy. We can begin with cosecant theta, for example. So if you look at this diagram, cosecant theta is the ratio of r over b. So I can write cosecant theta as r over b. Dividing by r, we get 1 in the numerator and b over r in the denominator. What is b over r? Well, b over r is sine theta. So with that, we have shown that cosecant theta is 1 over sine theta. Similarly, you could prove that secant theta is 1 over cos theta and cotangent theta is 1 over tan theta as shown here. So, very easy and effective way of proving the reciprocal identities. Now let's look into the other identity, and this time we'll take the quotient identity. Quotient identity is tan theta, the ratio of sine and cosine. Well, we can write sine as b over r from the same triangle, correct? So we'll refer to this particular point and our triangle, which we had been talking about. So in this particular triangle, once again, let me just draw it here. Okay, we know that this point P is AB. That means this is A, this is B, that is the right angle, that is R, and the angle is theta. So sine theta is the ratio of B over R, cos theta is the ratio of A over R and R cancel. Once you cancel R and R, you're left with B over A, which is tan theta. Similarly, you can prove cotangent theta is the ratio of cos theta and sine theta, right? So that is the proof, and that is how very easily, using a coordinate point, you could prove it. Now, the Pythagorean identities will again take up the same right angle triangle as we have been working with, right? So, in this particular triangle, we know these points are A and B when we are considering point A, B with an angle theta and that being R. Now clearly, we know a square plus b square is equals to r square in case of a right angle triangle. Now that helps to prove the Pythagorean identities, and that's how they get the name trigonometric Pythagorean identities. There are three of these. Sine square theta plus cos square theta equals to 1 plus tan square theta is secant square theta, and 1 plus cotangent square theta is cosecant square theta. So let's see how to prove it. Well, we can write this as b square plus a square equals to r square. If I divide by r square all the three terms, what do I get? I get b over r, but and square of that, right? B over r is sine, and square of that is sine square theta. A over r square means cos square theta, r square cancel, we get 1. So we get our first identity, which is sine square theta plus cos square theta equals to 1. I'd like you to pause this video, try it out yourself to prove the other identities. Basically, start with b square plus a square equals to r square, divide by different terms. If I divide by a square, I prove the second Pythagorean identity, and if I divide by b square, I prove the third Pythagorean identity for trigonometric functions. So I hope you find it very simple and useful. Correct. There are many other identities. One of them is a cofunction identity. Now, cofunction or complementary angle identity is something like this. When you're looking at a triangle from one side, the other side is 90 minus theta, correct? So, in a right angle triangle, if we have one angle as theta, the other angle here is what? Is 90 minus theta, correct? However, when you look from the other side, adjacent becomes opposite, opposite becomes adjacent, things flip. And therefore, you can say sine of 90 minus theta is cos theta, cos of 90 minus theta is sine theta, tan of 90 minus theta is cotangent theta, because they flip, correct? So that is the hint for you, and that is how you could do it. Sine A. Let us say this angle is A. In that case, sine A will be the ratio of CB over AC, right? But if you look from the other side, in that case, this ratio is of cos C, which is 90 minus A. And that shows that cos of 90 minus A is same as sine of A. And you can prove this particular identity. So that is the concept, right? Now let's take up another type of question which is very common in many test papers. We are not talking about the counter examples. The example here is provide counter example to show that sine A plus B equals to sine A plus sine B is not an identity. Well, to prove that the counter example, prove by counter example is very simple. You can take some value of A and B and show that these two sides are not equal, and therefore it will not be an identity. In our case, what did we do? Well, we took A as 30 degrees and B as 60 degrees. Substituting 30 and 60 on the left hand side for sine A plus B, we get 30 plus 60 is 90. Sine of 90 is 1, so we get a value. So left hand side is 1 for the taken values. Now, let's substitute the same 30 and 60 degrees for A and B on the right hand side. We get sine 30 plus sine 60. Sine 30 is half, sine 60 is square root 3 over 2, and that is definitely not equal to 1. Well, how did I get these values? You remember the special triangle? Very important to remember, right? 30, 60, 90. So if this angle is 60 degrees and that is 30 degrees, and we have a right triangle here, the sides are 1, 2, and square root of 3. So that gives you the value directly from this special triangle. However, for this particular case, it becomes a counterexample. We took some values for A and B, and both the sides were not the same, and therefore it is not an identity. Is that clear to you? Let's move forward. Now, here is another type of question which you will definitely see is to identify mistake in the work done. This is basically a communication question which you'll always see in a test paper. Now, the question here is steps are shown below to prove that sine theta equals to 1 minus cos square theta square root is an identity. Find the mistake and provide a counterexample to show that the trigonometric equation is not an identity. Well, the steps are we begin with an identity which is sine square theta plus cos square theta equals to 1. As you know, it's a Pythagorean identity. You could rearrange it taking cos square theta to the right hand side and then you could square root. So once you square root, you get 1 minus cos square theta. Now we are trying to say that sine theta equals to 1 minus cos square theta is also a trigonometric identity. Is that true? We know it is not, since we know that sine theta could have negative values. However, the right hand side will only have positive values, correct? So showing that this is an identity, so that something is wrong at this step. So the step mistake here is that whenever you do square root, you should have written here that sine theta is equals to plus or minus 1 minus cos square theta. Now it becomes an identity. So here is a mistake. You should have put plus and minus. Remember, whenever you square root, in that case, you have to write plus and minus. Is that clear to you? The other thing is, when you square root both the sides, what is square root of x squared? Well, square root of x squared is absolute value of x. So you could have done the other way also. Square rooting, you could have done either like this, or you could have written absolute value of sine theta is equals to square root of 1 minus cos square theta. That will be an identity. You get the idea. So these two could be identities. So I'll prefer the second statement, which is absolute value of sine theta is equals to 1 minus cos square theta within square root. That is an identity. You get the idea. That is why I had asked you this question. Is square root of x square equals to x? No, it is the absolute value, right? So this step is wrong, and here this value should have been the absolute value of sine theta. You get the idea, right? So that is how it should have been done, right? Right hand side in this case is always positive. Square root of something is always positive. So how can we leave that as negative? So we have to take absolute value. Clear? Now the second part of this is to provide a counterexample. We could have done it with counterexample. So let us take some value of theta. Now we know very clearly that sine is negative in quadrant 3 and 4, right? So from the rule, all are positive here. Sine is positive in quadrant 2, tan in 3, and cosine in 4. So if I take any value of theta in quadrant 3 or in quadrant 4, I will get a negative value of sine, and that will show that this is not an identity. So that is what I did here. I've taken a value of theta as 240 degrees. When I substitute 240 degrees to the left side, I get sine 240 degrees, which is minus half or minus zero point 0.5. On the right hand side, when I substitute, I get plus half, and those values are not equal. Therefore, it is not an identity. Is that clear to you? Perfect. So we have done the foundation. So we've seen how we can prove some simple identities using just a point in a coordinate plane. And using that point, we could also prove many identities. We have also seen the use of counterexamples. Now, let's begin with some more examples. Here is the one. Question number 3 for you is to prove trigonometric identities by rewriting in terms of x, y, and r. We are given a triangle here, the sides being x, y, and r. Now in this right angle triangle, sine theta is y over r, cos theta is x over r, tan theta is y over x, and r is square root of x squared plus y squared, right? That you know. Sine SOHCAHTOA is the ratio of opposite to hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. And that helps you to understand this. Now the thing is, we need to prove these identities. 4 of them are listed here for you. You can pause the video, answer this question, and then look into my suggestion. I'm going to adopt a very simple method to do it. So what we are trying to say here is, when we say cot theta is what? Is the ratio of x over y, right? So I could replace this with x over y. Sine theta is the ratio of y over r. right? So y over r. Now we can actually cancel out y and y. We get x over r, and we know x over r is what? Is cos theta. And so we have started with the left hand side, right? And we have shown that this is equal to right hand side, right? So these are the steps to be followed, and then you derive at the result which is same as the right hand side. Once you do that, that means you have shown that the identity is correct. That is how we prove it. Correct? So that is how you're going to prove all four of them. Correct? So I like you to pause the video, answer this simple method, adopt it, prove, and then look into the solutions. Here's a quick solution for all of them. The very first one, which I just did, cotangent theta times sine theta equals to cos theta. Cot theta can be written as x over y, sine theta as y over r. When you cancel, you get x over r, which is cos theta, same as the right hand side. So you have shown the very first one. Now 1 plus sine theta over sine theta is y over r. Writing y over r here, simplify by taking common denominators. We get y plus r over r, and then this gets like multiplied, right? And then you can cancel the r's and you get your expression. Dividing by y, rearranging, you can show the right hand side. Simple as that. So you see how effective it is to use the simple triangle and prove the trigonometric identities. And that is the general point, and therefore this identity works for all values of x and y. Let's take up the other two examples, which is 1 plus cot theta over cosecant theta sine theta plus cos theta. Replace cotangent theta by x over y and cosecant theta by r over y. Once you do that and simplify, you do get the right hand side. In the second case, secant square theta minus tan square theta equals to 1. We know r square is x square plus y square. Now what is secant? Secant is the ratio of r over x, tan is the ratio of y over x, right? Look at this particular triangle to write these ratios. Take the common denominator, which is x square, r square minus y square. As you know, r square minus y square is x square. Replacing it with x square, we get just x square over x square, which is 1. And therefore, we show this, that secant square theta minus tan square theta is equal to 1. Is that clear to you? Correct? Now, we'll look into the strategies, and based on these strategies, we are going to solve some of the trigonometric equations which we just saw earlier. Now, we are going to follow these four basic strategies to prove trigonometric identities. So, these important strategies are to be noted. First is rewrite the expression in terms of sine and cosine. So, whenever you see that there are tan, cotangent, secant, cosecant terms, write them as sine and cosine. And then it'll be easier for you to simplify. You could factor and then simplify. You could rationalize using conjugate of an expression, and you can take common denominator and then simplify. So these are the strategies which we are going to adopt to solve some of our questions. So I have taken very simple examples here to begin with. Example number 1 is tan theta over secant theta is equals to sine theta. Now, tan theta could be written as a ratio of sine and cosine. So once I write tan theta as a ratio of sine over cosine, you can see what happens. And secant as a ratio of 1 over cos theta. Clearly, I could cancel these terms, cosine theta, right? So you could write sine theta over cos theta equals to cos theta over cos theta, and then cancel, giving us the right hand side. And once we get the right hand side, beginning from the left hand side, which is this, right? We have shown that this is an identity. Left side is equals to the right side. Similarly, with 1 plus tan theta over 1 plus cotangent theta equals to tan theta, just replace tan theta with sine theta over cos theta and then simplify to get the result. So combination of these strategies work. Correct? Next example here is cos square theta plus cos theta over sine square theta equals to cos theta over 1 minus cos theta. Now in this particular case, you could factor. Cos theta is a common factor. And sine square theta can be written as 1 minus cos square theta and then factored as 1 plus cos theta and 1 minus cos theta. That becomes your strategy, correct? So that's what I've done here. So beginning with cos square theta plus cos theta, we actually took cos theta common. We got a factor cos theta plus 1. Sine square theta can be written as 1 minus cos square theta, difference of squares, as we started with 1 plus cos theta times 1 minus cos theta. Now here, you can cancel the terms which are common factors in numerator and denominator to get the right hand side. And you have shown that this identity is true. Now the same strategy is applied here. So these are to illustrate how beautifully you could use the strategies for simple examples. Now this could be done for any example, correct? 1 plus sine square x over 1 minus sine to the power of 4. You can apply difference of squares. You remember a square minus b square is equals to a plus b times a minus b. So we can factor the denominator. Denominator, which is 1 minus sine to the power of 4x, now could be now written as sum and product of 1 plus sine square x times 1 minus sine square x. Now clearly 1 plus sine square x cancel. Once you cancel that, you get 1 over 1 minus sine square x, which is, using Pythagorean identity, 1 over cos square x, and 1 over cos square x using reciprocal identity is secant square x. You may write the reasons also, correct? As you can see here. Next example here is to show what is square root of 1 plus cos x over 1 minus cos x. It is absolute value of 1 plus cos x over sin x. Now, in such cases, whenever you find square roots, you need to rationalize. So let us rationalize with the conjugate of the denominator. Denominator here is 1 minus cos x. So I multiplied by 1 plus cos x and divided by 1 plus cos x. Numerator becomes a perfect square in the denominator. It is difference of squares. But this difference of square is sine square x. So you get something which is like square root of x square, right? So this is equals to the absolute value. Remember, square root of x square is equals to absolute value of x. And that has been used to write down the result, which is your right hand side. Is that clear to you? So that is how you do it. Now, rationalization could also be done for simple expressions given here. This is a very important question, right? So let me just put a star here. We are using the same strategy of rationalizing, right? So we have to prove that 1 over cos x minus tan x equals to 1 plus sin x over cos x. Now, in this case, what I've done here is multiplied and divided by the conjugate of the denominator. Knowing fully well that a plus b times a minus b is the difference of squares, we get secant square x minus tan square x. And we know that is equal to 1, correct? You remember what is 1 plus tan square x? Well, 1 plus tan square x is equals to secant square x. We can rearrange 1 is equals to secant square x minus tan square x, correct? And that is what has been done. So we replace this by 1, and so we get 1 in denominator, and we are left with secant x plus tan x. Now you could convert to sine and cosine and get your result. Do you see the beauty of this, right? That is how we could very easily do it. Well, you could also convert this to sine and cosine ratios and then simplify. However, this is more effective way of doing it. Here is example 7. In this case, we have 1 over 1 minus sin x plus 1 over 1 plus sin x, and you need to show it to be equal to 2 secant square x. The second question is kind of reverse. 1 minus sin theta over cos theta plus cos theta over 1 minus theta is 2 over cos theta, right? Which is 2 cosecant theta. Correct. So, easy proof. Take a common denominator, multiply and simplify, you get your result. Same is the case for the next one. Just cross multiply with a common denominator. So the strategy here is common denominator. Perfect. So that is how you prove it. Now this is a very important example. I'll take this up later in solving trigonometric equation. Correct. So make a note of this. Correct. Okay. Now here is a worksheet where I've taken 6 questions for you. You can adopt the strategies, the 6 strategies which we learned to solve these questions. Perfect. Take a note of this, and then we are going to take solution of these one by one. Okay. Let's begin with the very first one, which is sine square x plus cos square y minus sine square y cos square x equals to sine square x minus sine square y. Look at the right hand side. Now it's very important to understand from where to where, right? So what do you need to do? You're looking at the right hand side, what you need to prove, right? So the question here is what you need to prove, correct? Keep that as a focus. Now on the right hand side, we have no cost terms, only sign terms. Do you see that? And therefore, the strategy here is to convert the cost terms as sign terms using the Pythagorean identity. So cos square y is written as 1 minus sine square y. Cos square x is written as 1 minus sine square x. Once you do that, then apply the distributive property, open the bracket and simplify to get your result. We get right hand side starting with the left hand side. So basically we began with left hand side and we landed to right hand side, and that is how you have to prove the identity. The only trigonometric identity we utilized here is sine square theta plus cos square theta equals to 1, which could be rearranged and written as cos square theta equals to 1 minus sine square theta. Correct? Let's take the next example, which is sine to the power of 6x plus cos to the power of 6x equals to 1 minus 3 sine square x cos square x. Now here you should know what is a cube plus b cube equal to. So the factored form is a plus b times a square minus ab plus b squared. In this case, you can write sine to the power of 6x as sine square x whole cube, cos to the power of 6x as cos square x whole cube. So in your case, what is a equals to? Well, a is equals to sine square x, right? And b is equals to cos square x. Replace that in the given formula and simplify. You get the idea, and you'll get your result. That is how you could prove this particular identity. Let's move forward to question number 3. We have sine square theta plus 2 cos theta minus 1 divided by sine square theta plus 3 cos theta minus 3 equals to cos theta over cos theta minus 1. How will you prove this? Well, we have only the cos terms. Do you see that? You notice only cosine terms, right? In right hand side. So what should you do? Clearly, you should write sine square theta as 1 minus cos square theta. Is that clear to you? And then you have your solution. That's what I did. So I have replaced sine square theta in both numerator and denominator by 1 minus cos square theta. We get a quadratic equation, right? So at this stage, fortunately for us, this numerator gets simplified to just a number, uh, those one getting cancelled. So we get minus cos square theta plus 2 cos theta. In the denominator, we have quadratic equation. Dividing by minus, we have cos square theta minus 2 cos theta over cos square theta minus 3 cos theta plus 2. Now here we need to factor, correct? So you need to factor and get your result as shown here. Cancel the common factors, you get the right hand side. And that is how you begin with left hand side and end up with right hand side to prove the trigonometric identity. Clear? Next question here is 1 plus cos theta over sine theta plus 1 sine theta over 1 plus cos theta is 2 over sine theta. Many times we may also write this as 2 cosecant theta. Is that clear to you, right? Anyway, so take the common denominator. So this strategy is common denominator. And then simplify as shown here. So just multiply and rearrange your terms and get the result. The next example here is tan theta minus cotangent theta divided by sine theta cotangent theta equals to tan square theta minus cot square theta. Now, in this particular case, we converted tan and cotangent into sine and cosine terms as we had done and got a result. You get the idea, right? So, converting is a good strategy to do. So that is how we are going to do it. Next example here is square root 1 plus sine x over 1 minus sine x plus square root 1 minus sine x over 1 plus sine x is 2 secant x. How do we do it? Well, the strategy here is to rationalize, correct? So in this case, you rationalize. So we are rationalizing both the terms separately as shown here, and then we are going to simplify to get the result as shown here. Is that clear to you? Right? So that is how we are going to get all these results. So I hope you have understood how do we prove these identities in different ways, correct? Now, I'll take a pause at this stage so that we could now go to the next level of questions. You remember in the very beginning, we had some examples, extended questions to do. Now, this is the set of questions which you are supposed to do. I'd like you to take a copy of this and then show that, rather solve the equations. So these are the four questions for you, and in these questions we have 1 minus cos theta over sin theta minus sin theta over 1 plus cos theta is tan 2 theta. That is an equation to be solved. You could actually simplify the left hand side. Once you simplify the left hand side, you might get some number, and that number equals to tan 2 theta will help us to find the solution to this particular equation. You get the idea. And that is how it could be solved. So I'd like you to pause the video now and then look into these solutions. Try to do them. Idea is to prove the left side as something and then solve the equation. Correct? So do it. Once you have done, then look into my solution. Correct? Here is my solution. I'm just giving you a quick solution to these particular questions here. So beginning with, again, we'll do the first one first, which is let's do this. Question number one. Okay. So the question here is 1 minus cos theta over sin theta minus sin theta over 1 plus cos theta equals to tan 2 theta. We need to solve this within 0 degrees to 360 degrees. So we'll first simplify the left hand side, prove this as an identity. So 1 minus cos theta over sin theta minus sin theta over 1 plus cos theta. Taking a common denominator, multiplying, and then simplifying, right? So when you expand this and then simplify, we get 1 minus 1 on the top and we get 0 on the top. Correct? That means the left side is equal to 0. Since the left side is equal to 0, the equation reduces to tan 2 theta equals to 0. And now we need to find a solution for tan 2 theta equals to 0 within the interval 0 to 360 degrees. You get the idea. Correct? We know tan 2 theta is between what? Well, if theta is between 0 to 360 degrees, 2 theta will be between 0 to 270 degrees. Correct? You know, period of tan is 180 degrees. Correct? And therefore, you can find all the solutions. We know tan 2 theta is 0 for 0. Keep on adding 180. Keep on adding 180 up to 720. So you get 1, 2, 3, 4, 5 solutions. Now divide by 2 to get the real solution, and that is how you solve this trigonometric equation. This trigonometric equation has a combination of solving an identity and then the equation. And the equation is also not simple. We are involving 2 theta, and that requires some more thinking. So it's a challenge extended question for you. Correct? Now let's look into the second solution, which is 1 plus cos theta over sin theta plus sin theta over 1 plus cos theta equals to 2 over cos theta. Right? So we have to provide a general solution in this particular case. Let's begin with the left hand side. So left hand side will take a common denominator and simplify. So once you simplify, you get 2 over sine theta for the left hand side. Well, the question is that the left hand side is equals to 2 over cos theta. This is not an identity, it's an equation. We are solving an equation. Therefore, we can now write this equation as 2 over sine theta equals to 2 over cos theta. Now it becomes simple. We can just cross multiply and we get tan theta equals to 1. We have to provide a general solution, right? So general solution for tan theta equals to 1. Tan theta is 1 for 45 degrees, correct? So, and also it has a period of 180 degrees, and that gives us the solution 45 degrees plus 180n. So every 180 degrees you just keep on coming and you get all your solutions which will lie in quadrant 1 and 3. Correct? So those are the strategies to be adopted. I've already dealt with you these two questions. Now here is the third one, which is cos theta over 1 minus tan theta plus sin theta over 1 minus cot theta equals to sin theta minus cos theta. We need to solve this equation. How do we solve this equation? Let's simplify the left hand side. So left hand side can be shown as equals to sin theta plus cos theta, and here is the proof for you, correct? So you can go through the proof here. We can show this as equal to, so left hand side is equal to sine theta plus cos theta. So basically, we will be solving the equation sine theta plus cos theta equals to sine theta minus cos theta. You get the idea. You can bring the terms together. It becomes so simple. Cos theta equals to 0, and we know cos theta is 0. For theta equals to 90, odd multiples of 90, right? Times 2n plus 1, where n is integers. You get an idea. So anyway, this is extended part. I've given you a glimpse of solving such questions. However, we'll get back to our basic concepts. Now, question number 4 and 5 are left for you to explore. So please explore these and see if you could really solve them. Correct? So with that, we come to an end of our video. We started with these trigonometric identities. We kind of proved them. We also took into counter examples to prove whether the equation given to us is an identity or not. We also looked into communication questions to find mistakes. And we had a couple of strategies to prove trigonometric identities. Even a point coordinate x and y could help us doing it. And then simple strategies could actually be very effective to solve any difficult question. With that, we come to an end of this video. If you really like and subscribe to my videos, that'd be great. Thanks for your time and all the best.